Welcome to a section on finding the matrix of a linear transformation. A linear transformation is nothing but a map from Rn to Rm that satisfies the same properties that matrix multiplication satisfies. Constants can come out, T of Cu is C, T of U, and the T distributes over addition. So again, matrix multiplication shares those same properties. In fact, this example here, if A is any m by n matrix, A is a linear transformation from Rn to Rm. Notice how the dimensions flip. The easiest way to see it is with an example. Here we've got a 3 by 2 matrix, A. It maps R2 to R3 by matrix multiplication. For example, A takes the vector 1, 0 in R2 to the vector, just multiply and you get 1, 2, 3 to this vector in R3. So a vector in R2 goes to a vector in R3. Here's a picture. R2 is called the domain of A. R3 is called the codomain. The codomain is not necessarily the same as the range. The range is the set of all B contained in R3 such that B is AX for some X in R2. And that may or may not be all of R3. So here we've got a theorem that tells us every linear transformation from Rn to Rm can be represented by an m by n matrix. And the way you find that, it's called the standard matrix. And the way you find that matrix is you just look at what T, the linear transformation, does to the standard unit vectors in Rn. So what we're going to do is focus on maps that go from R2 to R2 and find the matrix that corresponds to certain transformations. So let's start with reflections. So these are some just basic rules about reflections. If you take a point and reflect it about the x-axis, the x-coordinate stays the same and the y-coordinate becomes negative. If you reflect about the y-axis, then the y-coordinate stays the same and the x-coordinate becomes negative. If you reflect about the line y equals x, you switch the x and the y. And then finally, if you reflect around the line y equals negative x, not only do you switch x and y, but they both become negative. So negative y, negative x. So for example, let's say we want to find the standard matrix from R2 to R2, which reflects a point about the y-axis. So we always start with E1 and E2, the standard unit vectors in R2, and we see what T does to them. So if we're reflecting about the y-axis, T of E1 is going to flip over here. So E1 is going to get flipped over horizontally, and E2 is going to stay where it is because it's already on the y-axis. So the matrix A, we just write down the coordinates of T of E1 and T of E2. T of E1 goes in as the first column. That's negative 1, 0. It's T of E1. And T of E2 is 0, 1. That goes in the second column. Okay, use the matrix to find T of 1, 1. So T of 1, 1 is just the matrix A times the vector 1, 1. Okay, and that's negative 1, 1. Now, we didn't need a matrix to tell us that. Let's just look at the geometry. We've got the vector 1, 1 is right here. If we want to reflect that about the y-axis, it's just going to flip over here to negative 1, 1. And that's exactly what we got when we did that matrix multiplication. Okay, let's talk about projections. If we want to project onto the y-axis, then we're going to annihilate x. So 0, y stays the same. And if we want to project onto the x-axis, x sits there and y gets squashed. So x, 0. Okay, so for example, find the standard matrix of the linear transformation that projects points onto the x-axis. So again, we start with E1 and E2 and see what T does to those. All right, E1 is already on the x-axis, so T of E1 doesn't move. And then E2 is on the y-axis. That's just going to get crushed completely. It goes to the origin. So T of E2 is that single point. So the matrix A is 1, 0, that's T of E1, and T of E2 is 0, 0. All right, and let's use that matrix to find T of 7, negative 3. So T of 7, negative 3 is 1, 0, 0, 0, 7, negative 3, which is just going to be 7, 0. It kills the y coordinate. All right, and last transformation, we're going to talk about rotations. I've got a proof of this at the end of the lecture notes, but if you rotate a vector counterclockwise about the origin through theta radians, then the standard matrix is right here. So T of E1 is this first column, and T of E2 is the second column. So for example, if we want the matrix for a counterclockwise rotation of pi over 6 radians, then we want cosine of pi over 6 goes in up here, which is root 3 over 2. And then down here, we want sine of pi over 6, which is a half. And then negative sine of pi over 6. And cosine of pi over 6, root 3 over 2. So there's the matrix. You can do combinations also. And so these are fun, and we'll do these in class. Suppose we want to first reflect around the line y equals negative x and then project onto the x-axis. So here's E1, here's E2. The first thing I want to do is reflect around this line y equals negative x. So E1 is going to come down here. This is E1 prime. I can't call it T of E1 because T of E1 is the whole process, the last picture. This is the intermediate picture. E2 is going to come over here. So this is E2 prime. And if we project then onto the x-axis, E1 prime is going to get crushed. So now I can say that is truly T of E1, the origin. And then E2 prime just stays where it is. So this is T of E2. So our matrix A is 0, 0. That's T of E1. And then T of E2 is negative 1, 0. Okay, let's end with a talk about one-to-one and on-to. So if we have a linear transformation from Rn to Rm, it's onto if every vector in Rm gets hit by a vector in Rn. So this is the way you would say that. And it's onto if the range of T is all of Rm. So in my picture here, this is not onto because there's a vector here that's not getting hit by a vector in Rn, all right? And then T is 1-to-1 if for all B over here in Rm, there's at most one X that goes to that B. And so in my picture here, T is also not 1-to-1. Because this vector here gets hit by two guys over here, and that's not allowed. And so in theorems 11 and 12, I'm just going to summarize here. T is onto if and only if the columns of A, the matrix for T, span Rm. And I'll just remind you, the columns of A span Rm if and only if A has a pivot in every row. And T is 1-to-1 if and only if the columns of A are linearly independent. So AX equals 0 has only the trivial solution. Well, that happens if there's no free variables, so you have a pivot in every column. So here's just a simple example. Suppose T is a linear transformation with this matrix. Now this matrix is 3 by 4, so T maps R4 to R3. So R4 is the domain, and R3 is the codomain. Is T onto? Well, do we have a pivot in every row? Yes, we do. Is T 1-to-1? Do we have a pivot in every column? No, we don't. All right, and that is the end of this section.